Hello and good day to you. So today I'm trying to look at structural equation modelling. What you might infer from this video might be limited in terms of stuff you learn about R to, oh, you could do this, rather than some amazing new function that gives you something really powerful and different. And the reason, though, I think the fact that, oh, you can do this is really powerful and gives you an insight into ways people use linear regression in much more complicated places than what we're doing. So structural equation modelling is the idea of, I might have a concept, and I think the most famous use of structural equation modelling is in the social science, but also in IQ. So if you think about IQ, it's a very complicated concept of intelligence. We don't know how to measure intelligence in the way we measure wood. We can't get a measuring tape out and measure it. So we can't really, it's always going to be debated whether IQ is a real measurement of intelligence or not. And if you go to the Wikipedia page, you will see huge amounts of arguments and a huge amount of history of people talking about it. I don't want to get into that. I've read interesting cases on both sides. One where it says it's just a fair and even median assessed statistic of certain behaviours, and the other one where it says, well, at the end of the day, the map is not the territory, and you might be building a map, but you have no idea about the territory when it comes to intelligence. And I would advise, before getting into the IQ flame war, that IQ has amazing list of graveyard of ideas that is very scary, but it's a really great way for us to explain structural equation modelling and get our heads around the concept. Now, I can't get a measure of intelligence, can I? It can't be measured, in the same way we measure the length of a piece of wood. But what I might do is I might say, well, I have some descriptors of intelligence, and in the usual general IQ model, you have verbal comprehension, working memory, and perceptual organization. Now, those three things are also difficult to measure, but they're a bit closer to measurable. So then for verbal comprehension, we split it down into vocabulary, similarity of words, information, comprehension. For the working memory, then split it down into arithmetic, digital span, letter and number recognition. Perceptual organization gets split into digital symbology, symbol search, matrix reason, block design, and picture comprehension. Now, we can give to the user a set of questions that assess their ability in the bottom level of those areas. And the idea here is, when you come to social science things like, is this person going to buy a Netflix account? You could just do a regression and say people with these markers are more or less likely. But one more complicated way of doing it is to say, well, what is that behavior in terms of symbolic thinking, and then break it down into layers, and then group up those equations. So, in the case of IQ, verbal comprehension, is your marks between those subjects that make up verbal comprehension. Working memory is your marks between those subjects, and perceptual organization is marked between those subjects. And then general IQ becomes a weighted measure between those three. And within the modern measures of IQ, we've kind of given up trying to find an eternal perfect model, I believe, and we just median assess, and your intelligence is how many standard deviations you are away from the center, which does mean that what we think of as intelligence in quotation marks is continuously changing, which means that we it's really it's really complicated if you start thinking of it as a real thing, but not so when you think of it as just a piece of maths that's to give a rough estimation of behaviors between different people. And you can see why the social scientists love this and find it useful, because if you want to measure likelihood of depression, things like that, you will want to break that down into a set of behaviors, feelings, and then find data-based assessments that link back to those feelings as your starting point to building a theory of what causes depression. So you can sort of see social science, you start with a something that's very nebulous that you want to measure, you break it down until you can measure it and turn it into real data. Pardon me. So the library you need to use is SEM, Sierra Echo Mike. You will want to import the data cline, Kilo, Lima, Echo, India, November. And this is a set of economic data. There's a bunch of formulas that split between these different data sets. And this is, so first one is it uses lag, so it uses some information about last year. As you can see, the p value of last year and the x value, which we've named p lag and x lag. And then I'm going to make 3 equations. Now, when I said you're going to learn only one small thing about R, and it's just going to be, oh, I can do that, well, you might have just thought that all you can do is put plus, plus, plus of lots of different values. You can actually group them up. And in fact, there's nothing stopping you doing stuff like, that's a capital C, P times P, that's a capital P. Oh no, I need to do it cline. See, sometimes you get things wrong. But as you can see, you can do your linear regressions as if you're multiplying things and doing it as you would do an algebraic equation. So you might have been thinking you just have to keep on using the plus value. You can use brackets, you can divide stuff, you can add in log values. You can treat it as if you're writing a algebraic formula, and anything you did at high school with algebraic formulas where you wrap stuff in functions. I think there might be some exceptions to that, but as far as I've found so far, you can happily do it in one way or another, and that lets you represent your structural equation models in R, which lets you tackle problems and processes you might not have even touched at all. Because if you think about it, if you like in our previous example of depression, there's no way you could do that with a standard linear model. But by grouping up these behaviors, and then, you could eventually, I'd have to show you stuff about logistic regression, how you turn it into a percentage rather than just a value between 1 and whatever. But you can sort of see how you sort of, when it comes to more nebulous concepts which you're not so certain about, how you can still, using a trial and error method, you get there with a linear regression. And in fact, even make a linear regression possibly quite unlinear if you start adding in powers and stuff. So I hope that's helpful. I know that's really, really simple view on structural equation modeling. It's so much more complicated. There's a whole thing about path analysis that defines what those things might be in more complicated methods of doing it. But hopefully that acts as an introduction, and I could just carry on with linear regression and keep on trying to do harder and harder concepts within it. But it feels like by showing you this, I've showed you some of the more interesting methods of where you can break down a problem and turn it from a social problem into a maths problem that can then be analysed statistically. And then hopefully, if you're really good, and I think you do have to be really good and really scientific and mathematical, and go through your process carefully, you could potentially solve all three of those problems with one equation. And that's interesting. So thank you for that, and have a good day and a good night. Bye.